Hello, I'm Hannah Sachs, Editor-in-Chief of NEJM Evidence, and this is StatStat. You just rang in the new year, and your New Year's resolution is to get fit. You decide to sign up for a 5K and download a popular workout app to start your training. But is it really that simple? Surely more training will make you faster, but by how much? You realize figuring this out should be straightforward. You need to examine the strength of the relationship between a predictor variable, time spent training, and an outcome, race time. This is starting to sound like the regression chapter of your stats textbook. Regression describes the relationship between outcome and individual predictor variables. When the outcome of a variable is continuous, here the time to run a 5K, linear regression is used. Predictor variables can be continuous, time spent training, binary, whether you listen to music when you run, or categorical, different shoe brands. Simple regression is when there's only one predictor variable. Multiple or multivariable regression is used with more than one predictor variable. Linear regression finds a straight line that best fits the association between predictors and the outcome. You need some data, so you head down to the park to scout a 5K race and investigate the relationship between race time and hours training. At the start line, you survey racers, asking them how many hours they spent training per week. You know what shoes they have on and whether they're listening to music. And then you record their times as they cross the finish line. Afterwards, you jog home to analyze the data. It's important to check if linear regression is an appropriate way to analyze your data. Let's dive into 4 key assumptions made when applying simple linear regression: linearity, homogeneity of variance, normality, and independence. Assumption 1 is linearity. There must be a linear relationship between the predictor and outcome variable. You can check that by examining a scatter plot. Here you see that there does appear to be a linear relationship between the time spent training and the time needed to run the course. Assumption 2 is homogeneity of variance. To check this and the other remaining assumptions, you use the residuals. The residual is the difference between the observed value and the value predicted by the regression model. And if the model fits the data well, the sum of all the residuals should be pretty close to 0. The variability of the residuals should be constant across different values of the predictor. Looking at the plot, the magnitude of the scatter appears constant, so these data appear to meet this assumption. Assumption 3 is normality. The residuals should be normally distributed centered around 0. Here, that checks out too. Assumption 4 is independence. Independence means that the residuals are not correlated with each other. This can be checked by plotting the residuals and checking to see whether there are clusters or patterns. You see none here. Simple regression seems, well, simple enough. But many other things other than hours spent training could affect your race time. Do the right shoes make you run faster? The right pump-up music? To examine multiple predictor variables, you need multiple regression. You still need to check your assumptions, which is just a little more complicated. Also, when you have multiple predictor variables, it is important to understand how correlated the predictors are, as their inclusion or exclusion could change the importance of other predictors. For example, here you have a variable indicating whether or not a runner listens to music. You should, of course, not also include a separate variable indicating whether or not a runner is using headphones. Confident that these assumptions seem to hold, you're ready to move forward with multiple linear regression to describe the relationship between training time per week and the time needed to run a 5K, adjusted for the differences in race time due to shoe brand and whether the runner was listening to music. Your results show that every added hour training per week was associated with a 2-minute improvement in race time. Impressive! You also find that running with music was associated with faster times compared to running without music, but there were no apparent differences in race time associated with sneaker brand. While it might be tempting to try out some other predictors in the model, outfit color, pre-race breakfast, time spent stretching, you don't want to overfit the data. Overfitting occurs when too many predictors are included in a multiple linear regression model, so the model fits the data so well that if you try to use it to evaluate the same outcome in a new sample, it won't work well. It's best to pre-specify predictors based on a plausible rationale. You also shouldn't extrapolate outside the limits of the observed data. You can't, for example, use these data to imply that if you trained for 20 hours a week, you'd beat the 5K world record. The relationship between training time and race time is probably very different in a sample of elite athletes. So all in all, based on your analysis, you conclude there are no shortcuts and fancy shoes won't make you faster. You dig deep, put in the hard work of training. And now with your new playlist ready, you head to the starting line.